Initial presentations, I'm not sure what I'm going to talk about, so jokes apart. I'm going to talk about Grafana Loki, which is an open source solution to collect and query application and system logs at scale. December 2018, David Kalschmidt from Grafana Labs was on the stage of KubeCon North America to announce Loki, this new open source solution to collect and query logs. Fast forwarding a year and a half later, today Loki is generally available and is used by many companies and users as a logging solution. To give you an example, at Grafana Labs we also use Loki for our internal applications and systems. We currently ingest about 22-25 megabytes of logs per second for a total of 2 terabytes of logs on a daily basis. Last week, my colleague Cyril was tweeting about some performance improvements we are continuously doing in Loki. In our internal cluster, we are now seeing almost 10 gigabytes of 10 gigabytes of logs per second scanned at query time. So, for example, it tried to run a query which processed about 420 gigabytes and it executed the query in 45 seconds, which I think is pretty cool. My name is Marco. I'm a software engineer at Grafana Labs. I'm a Loki contributor and user, and I'm also a Cortex maintainer. I'm mentioning Cortex because even if Cortex is a distributed storage for Prometheus, so Cortex stores the metrics, Loki stores the logs, they actually both share most of the architecture. So Cortex contributors frequently contribute to Loki and vice versa. The typical problem we have is a distributed system composed by many applications or microservices logging tons of logs, and we want to collect and store those logs in a cost-affordable way. The way Loki solves this problem is through an agent called Prometheus, which you install on each node where your applications are running, which tails the local logs, so system logs, application logs, and push those logs to a central server, which is Loki. And then you use Grafana, the dashboarding tool, to query those logs or to graph those logs. Or we can also provide a command line tool called log CLI to query those logs from the CLI, from the terminal. Before going deeper into Loki, it's better to focus a little bit on the log anatomy in Loki. So when you collect logs in Loki, a single log line, a single log entry, is composed by 3 components: a timestamp, a set of labels, and the log line, which is the content of the log. The labels are key value pairs, which you can set in the Prometheus style, so it's the name of the label equal the value, and you use to attach metadata to your logs. Like you can use the labels to set the application name, which is logging, or the node IP, or other informations which you can get from the system, which is logging. The trade-off picked by Loki is to not index the log content. So we do not index the entire content of the log, but we just index the timestamp and the labels. This means that at query time, what we do is, given your query, we do filter down all the logs by the time range and the label matches you set in the query, and then, given the resulting logs, we do further scan the entire log content in order to filter based on the log line or the log content. A group of logs with the same exact set of labels is a log stream. So at the end, you will have a bunch of log streams in parallel. This is important because Loki has picked a second trade-off. Given a single log stream, the log entries must be pushed to Loki already sorted by timestamp. This means that Loki rejects out-of-order logs. This is an important trade-off for performance, which we picked for performance reasons, because in this way, the logs we receive on the server side are already sorted by timestamp, and we don't have to do any reordering, both at ingestion time or at query time. Don't get too much scared about this sort of limitation, because actually the agent, Prometheus, can help you fudging out-of-order timestamps. So if for any reason your application is logging out-of-order timestamp, Prometheus can be configured to fudge, like fake, the out-of-order timestamp in order to not get the logs rejected on the server side. This is optional. You can configure it or not. At query time, when you run a query, you actually specify two different things. The first one is the time range, like the last 1 hour in this case. And the second one is your log query. The log query is composed by two parts, the log selector and the filter expression. The log selector filters the log streams matching the labels. If you are familiar with Prometheus, the log selector is the exact same of the Prometheus label matcher. So you can match the labels by equal, by regex, or not equal, not regex match. The log selector is executed using an index, which means actually it's pretty fast. And then, given the resulting logs, we do further filter down the logs based on the content. So if you specify an optional filter expression, what we do is to scan all the matching log streams in order to find only the logs which match your filter expression. In this case, we match all the logs containing the word error, but not containing the /5icon.hypo. In other terms, means we just built a distributed graph, if you think about it. Prometheus, the agent which is used to push the logs to Loki, does three main things. First, it discovers local logs running on this node. It can be the system logs, it can be application logs. And then, for each log line, which we call log entry, you can configure a pipeline to process those logs. You can process those logs to attach labels or to transform the log, to remove part of the log. And then at the end of this processing pipeline, Prometheus push the logs to Loki. Now, Prometheus is not the only way you have or you can use as an agent. We do support alternatives. We have plugins for FluentBit, FluentD. We also provide a Docker driver, which you can directly plug into Docker in order to push all the application, all the container log to Loki. But in this presentation, I will show you Prometheus. One of the most interesting things to me about Prometheus is the built-in service discovery. Prometheus supports two Prometheus-style service discovery, the static one and the Kubernetes. Now, the static service discovery is common to probably any other logging solution. You just configure a set of paths on the file system from which Prometheus should tail the logs and push them to Loki. Pretty simple. The Kubernetes one is more interesting if you run on Kubernetes, if you run your application on Kubernetes, and what you want to do is to push your pod logs to Loki. Because when you configure the Kubernetes service discovery, what Prometheus does is to continuously communicate with the Kubernetes API to automatically discover the pods running on each node and to allow you to dynamically attach labels to the pods, to the logs of each pod. For example, you can attach the pod label as log label, or you can attach node metadata, like the node IP or the node name, as a log label. And this can be configured to be dynamic. So if you deploy new applications as pod in Kubernetes, all those labels will be automatically injected to each log before getting pushed to Loki. There are three main ways to run Loki. The first one, and the easiest one, is the single binary. So Loki is provided as a single binary. It's just one binary, you download it, and you can run it. It's usually suitable for small installations, like you want to try it on your computer, or even if you want to run it in production, you can actually use the single binary with a shared storage or a reliable storage. And it's the operational mode I'm going to use in the demo I will give you in a moment. The second way to run Loki is the so-called Microservices Way. So basically, it's the way we use to run Loki at scale for large installations. And the main difference is that when you run Loki in a single binary, what we do within a single process is actually running multiple services, okay? They are hidden to you, but inside this process we are actually running multiple processes which compose the microservices architecture. In the microservices architecture, you can actually deploy each of the Loki services on different nodes, and you can horizontally scale each of those services individually. The third way is not running Loki by yourself, but is using Loki as a service. Grafana Labs offer a solution which is called hosted logs. And when you use hosted logs, what you actually do is just configuring Prometheus on your nodes, and you push your logs to Loki managed by Grafana Labs, and you get an endpoint that you can configure in Log CLI or Grafana, the dashboarding tool, to query back your logs. In this demo, I'm going to show you the single binary. Will be a pretty quick demo. Let me show you how I set up the demo. So I downloaded the latest stable release of Loki from the GitHub release page. And I have on the system two binaries, the Loki binary and the Prometheus binary. Loki is the server, Prometheus is the agent. And then I built a simple script, bash script, to generate random logs just for the demo. So let's say the information inside the log will not be much useful, but it's just for give you a demo. It logs 10 logs per second, so pretty small. And the log format is in, I don't know if you are familiar with the Golog format, it's like a key value as well. So the log format is timestamp equal the timestamp, the level, and then the log level, like info or error, and then the application name, and then the message content. I configured Loki using the local file system as a storage. So we are not, in this demo, we are not going to use any shared storage you actually use when you run Loki in microservices mode or in production. And I configured Prometheus to scrape using the static service discovery. So I'm not using the Kubernetes service discovery. I don't even have Kubernetes running on my laptop. So we are scraping a file called simulated.log, which contains the fake logs. I have a regular expression parsing the log line and extracting the timestamp, the level, the application name, and the message content. I'm setting the log timestamp based on the content of the log line, the labels, the level, the log level, and the application name based on the content of the log line. And then, since we don't need to keep the timestamp, the level, and the application name because we already script them and set as metadata. I'm just replacing the log line just with just the content of the message. So I already have the script running which logs random logs. And we are now going to start Loki. And we are now going to start Prometheus. So at this time, we have Loki running on my network. We have Prometheus, which scrape the fake logs and push them to Loki. I have a local installation of Grafana as well to query this log back. So now we are going to have the data source. We selected the type Loki, and I configured the local endpoint. Okay. And now, oh sorry, I maybe too quick. Grafana has a panel called Explore. I don't know if you are familiar with Grafana. Grafana is a dashboarding tool, so you can actually build dashboard, you save them. But there's this Explore panel, which is very useful if you want to run manual query, whether they are metrics or in this case logs. So I'm going to use the Explore first. I select the data source, which is Loki, and the Explore panel. The two things we actually care about the Explore panel in this demo is the time range. Now it's last 1 hour, and the input box where we type down the query. So let me select a more recent time range. Okay. So when I configured Prometheus for all the logs scraped from my simulated.log file, I've also configured to always attach a label called type demo. This allows us to query all the logs we currently have. So the result we get is a list of logs down there, which we can scroll, and an histogram. Here, the histogram shows you the logs as a stack splitted by the log level. The script which generates the fake logs generates some errors and some log with the info level. Now, if you scroll down, here you can see all your logs. We have the timestamp, which we can hide, and we have the log line. If you click on a single entry, you actually get the details about this specific log line. We can see that the backend application was logging this line, the level is info, and yeah, it was scraped from this file, and this is the timestamp. So let's say that we want to look for the errors. What we can do is to further filter the logs by error. In this way, what we get is just the error logs. Now, let's say that we are interested into the errors related to the login and logout. So what we can do, since the login and logout are not labels, but they are the content of the log line, we can actually write, we can actually add a filter expression to further filter down the logs based on the content. So for example, we can filter all the logs containing login. And here we are, all the login. Is it too small? Can you see it? Yeah. Now let's say that we want to filter by login and logout. What we can use is a regular expression with a node. So I change from the equal matcher to the regular expression. and we are looking for login or logout. And what we get now is a mix of logins and logout. You can further filter them. And let's say that we just want to see the entries for the user 90. Then I pick only the log lines containing user 90. I guess you can understand how the query language works, right? Even if those logs are just fake logs, not much useful. Now, the other very interesting thing of Loki is that it allows you to generate metrics based on logs. So on the top, there's this switch button, and you can actually switch to the metrics. So if here I switch to metrics, I can write a query to extract metrics from the logs. The way it works is using aggregating functions. And Loki supports Prometheus-style aggregating function. So if you are familiar with Prometheus, you will probably know the function rate, which in Prometheus gives you the rate per second of your series, the time series value. In Loki, it gives you the rate per second of the logs, matching the query inside the brackets. So for example, if we do rate type demo 1 minute, the result is for each log stream, and right now we have 4 log streams. I will show you in a moment. It gives you the logs per second logged by each log stream, calculated over 1 minute time window. So each data point we have here is the rate of the logs over the previous 1 minute. And it's a sliding window, right? Like this. We currently have 4 log streams, which we see here. It is too small. Yeah. We have the application API with the level error. We have the application API with the level info, the application backend with the level error, and the application backend with the level info. It's the combination of labels attached, logged by my script. Okay. And what you can do, let's say you are interested into the logs per second splitted by the level. So across all your application, you just want the sum by level, by log level. What you can do is to sum the rate by level. Sorry. Okay. Is to sum the rate by level. So what we got now is the rate of logs per second by the level, error level or info level. That's queries. With less queries, we can actually build dashboards. So I switch to the dashboard panel, and I create a new dashboard, and I add a new query. So let's pick this. I copy and paste, and what I get is the rate of log by level per second. And we can add a second panel to show the actual log. So you can, in a single dashboard, you can have the metrics extracted from logs and the single log entries side by side. We pick the log panel, and I type down the same query, but removing the function used to extract the logs. Sorry, to extract the metrics. And what we have here is side by side the logs and the same logs but graphed based on the rate of logs per second. If you change the window, like selecting, oh, okay, you are, okay. If you change the window here, the time range window, both the metrics and the logs change accordingly. So, are you still with me? Yeah? So, after this quick demo, if you want after the talk, if you have any question, I can show you more features. I would like to do a deep dive into the Loki architecture and storage. So far it was a black box, right? I told you, well, we have a Loki server, but we didn't look what's inside the Loki server and how it works. I will try to make it as much simple as possible. When Prometheus push the logs to Loki, it follows the write path. The entry point of the write path is a service called distributor. The distributor does a validation of the input logs and shard and replicate those logs across a pool of ingesters. You can see the distributor like a proxy, like an intelligent proxy. The ingester keeps the received logs in memory and build up chunks of compressed data. So all the logs received are compressed in memory into chunks of data. Each chunk, a chunk is just a buffer of compressed data. Each chunk is complete. The chunk gets flushed to a shared storage and offloaded from the ingester memory. At query time, when with Grafana or with log CLI you run a query, the entry point is the query. What the query does is, given the query time range and the query expression, it both query the ingesters and the shared storage to get the chunks of data matching the label selectors. The querier receives all the chunks of data matching the label selector and decompress in memory all the logs in order to scan the logs and filter down based on the filter expression, which is not indexed. So far, the storage is yet another black box. So let's look how the storage works. Each log stream, as I previously mentioned, is stored into chunks of data. Each chunk contains the compressed log entries for a specific time window. So let's say we have two log streams. The Nginx application running on 2 nodes, we have 1 log stream per node, per Nginx application. Given a time window, like between the T1, the time 1, and the time 2, the ingesters create a chunk for each of those log streams. And then, when the chunk is complete, it's flushed to the storage and a new chunk is created. And so between T2 and T3, another chunk of data is created. And then between T3 and T4, another chunk of data is created until it's flushed to the storage. And so on. If we look inside each chunk, the chunk contains the log lines, the log entries, already sorted by timestamp. Remember, it's by design. Loki requires that the input log lines are already sorted, right? So if we look inside each chunk, we have the log lines for each log stream sorted by timestamp. And since they are already sorted, we don't need to index every single timestamp, right? We just index the minimum timestamp and the maximum timestamp. If you have the minimum timestamp, the maximum timestamp, and the data inside is sorted, you can binary search inside. The chunks are filled up is the write path. When from tail push logs to Loki, it hits the distributor and then the logs are pushed to the ingester. When the distributor receives the input log streams, we mentioned before that what it does is sharding those log streams across multiple ingesters in order to be able to horizontally scale the write path. What it does is, given the label set of a log stream, it generates a hash, and based on the hash, it picks the ingester where those logs should be written to. Now the question is, what happens if an ingester dies? Remember, the ingester keeps the logs in memory until they are not flushed to the storage. And the logs can be kept in memory actually also for a long time, sometimes even several tens of minutes, or in some cases even hours. So if an ingester dies, unfortunately, all the memory logs are lost. There's no black magic. But there's a solution. Replication. Loki allows you to configure a replication factor, which means for each input log stream, you can configure on how many different ingesters the logs should be written to. We suggest a replication factor of 3. So that if an ingester dies for any reason, the same log is also stored in other 2 ingesters. The replication and the sharding is based on the ring. The ring is a distributed data structure we use to evenly share the logs across the pool of ingesters. The way it works is the hash I was mentioning before in Loki is a 32-bit. Okay? But just for the sake of this presentation, let's assume it's a number between 1 and 10, just to keep it simple, right? So we have a key space. Our key space is each number between 1 and 10. 1, 2, 3, 4, 5. when you start an ingester, the ingester picks a random value. Just use the random function to get a random value within our key space. In this case, between 1 and 10. The ingester 1 picked the number 2. And then you start another ingester, like the ingester 2, and it picks the number 6. And you start a third ingester which picks the number 9. They are a random number, okay? Now, when the distributor receives a log, we compute the hash of the labels, as mentioned before. And the hash is a value within our key space. In Loki, it's 32-bit. In the demo, it's between 1 and 10. Let's say that the hash of this log string is the number 3. What we do is looking within this ring if there's an ingester with the number 3. If there's no ingester with the number 3, we start walking the ring clockwise until we hit the first healthy ingester, which in our case is the ingester number 2. Now, if you enable the replication, and let's say you set a replication factor of 3, what we do is to not stop walking at the first ingester, but we continue walking the ring until we find 3 different healthy ingesters. And the log is pushed to those 3 ingesters. The ring data structure, since it's shared across all the ingesters and the distributors, need a shared storage as well. We support console, etcd, and we recently introduced support for gossip, which means that with gossip, which is still experimental, you don't need to run yet another dependency, yet another backend. Loki can create a peer-to-peer network between all the services, so between the distributors and the ingesters, so that they can communicate each other and propagate the changes to the ring data structure. Now, don't get too much scared about this requirement, because actually no strong persistency is required. To give you an example, we run Loki with console just using 1 instance in memory. Why? Because if you lose your console data or you lose SC data, and you restart console from scratch, like console is empty, Loki is able to reconstruct the data of the ring without affecting the service. So even if console is down for a short time, Loki can continue running without any noticeable difference from the external perspective. There will be much more I would like to talk about, but I obviously don't have time and I don't want to be too much techy. Just to mention a couple, we actually have 3 layers of caching in order to reduce the operations against the storage, both on the write path and the read path. Obviously, the storage can be the most expensive part when you run Loki, because you are supposed to store a bunch of data. We do support memcached to cache the data between the Loki services and the storage. Loki is also multi-tenant, which means you can have multiple, you can fully isolate logs by tenant inside Loki. So think about teams. You are in a big company and you have multiple teams, and you want the team A to just query the logs of the team A, and you want the team B to just query the logs of the team B. If you configure the team A and the team B to be 2 different tenants in Loki, their data is fully isolated, and the team A can't query the data of the team B for any reason. And the multi-tenancy is the way we run Loki as a service. So we actually have large Loki clusters running a bunch of customers, but each customer data is fully isolated. Before leaving, or before, let's say, ending this presentation, there's one last thing I want to talk about, which has been recently introduced, and it's the query frontend. Now, the query frontend is an optional service you can put in front of the query and can be used to speed up the query performances. It does two main things. The first one is a fair scheduling. Now, let's think for a moment what happens when you don't have the query frontend. When you don't have the query frontend and you run multiple queries, what happens is you usually have a load balancer, and the load balancer does a round robin in front of your queries. So you run a query, hit the query number 1, and then you run another query, hit the query number 2, and so on. It does a round robin to distribute the traffic. The problem here is not having query put the same workload on the query. If you run a query on a very small time range or hitting very few log streams, it's a super fast query, like it runs in 100 milliseconds. And then you run another super heavy query, which maybe takes 30 seconds, right? If you do a round robin across the queries, you may end up with unbalanced traffic. Your query may hit a query which is already processing a very heavy query, so it doesn't have any idle resources, while you still have another query which is idle. No query is not executing any query. With the query frontend has an internal in-memory FIFO queue where we put all the queries that we do receive. So for each query we do receive, we put the query into the queue. And then the first query, which is idle, which is not executing any query, picks the query from the queue and executes it. In this way, we actually get a better scheduling of the input queries. The second, and even more interesting thing, is query parallelization. The nature of Loki make it possible to easily parallelize the execution of one single query. So let's say that we have one query. This is the query from the example I gave you at the beginning, with a large time range. Like you want to run this query, but for 24 hours time range, right? What the query frontend does is to split this 24 hours query into 24 one-hour query. So instead of one query with 24 hours time range, we do internally execute 24 queries, each one with 1 hour time range. So we put the 24 queries into the query frontend queue. The multiple query, the pool of queries will pick the queries and send back the result to the query frontend, and then the query frontend merge the result, all the result, and return back to the client all the logs sorted by timestamp. That's pretty much all for this presentation. I hope you enjoyed it. If you have any question, I will be very happy to answer. If you don't, I'm available after the sessions. And that's all.
We can Loki process not well-formatted logs. Also, when I have some application written by someone else and I can't tell him, please rewrite log system because I want to use Loki, okay? He does have another job, but he has some very ugly login. He's I think not very well time format and etc. Can I process this with Loki also?
Mm-hmm. Yeah. So the question here is, if I can't configure Loki to parse the log line, right? Because the log line is random, it's not formatted. It's not structured logging, let's say. Can I use Loki anyway? Yes, you can. So, the labels can be set in multiple different ways. You can actually also parse the file system path if you use the file system service discovery to extract the logs, right? Or if you use the Kubernetes discovery, for example, at Grafana Labs, we use the Kubernetes discovery, we don't even parse the log line, right? All the information we do attached to the logs are already coming from the Kubernetes API. So yes, you will not parse the single log line, you will not extract information or labels from there, but you can still extract information from the system.
Okay.
Does that answer your question?
And when one log line is spread across multiple lines, can we build it with Prometheus?
Yes. So the question here is, if one log, is there multi-line support into Prometheus? So what you are talking about is not Loki, but it's Prometheus. We are working on it. It's a pretty common use case. The most common use case are exception traces, right? Your application panics or there's I don't know, a seg fault. The output is multi-line, right? Yes, it's a pretty common question. We are working on it, which means we attempted a few times to build it in the right way. We actually want to make it as much easy as possible to use for the final user, right? Because it's a thing that can be quite complicated. And we are actively working on it. I do expect we'll be ready soon.
How's the performance of S3 versus something like Dynamo or Cassandra?
Okay.
And which one is more common?
Huh.
And which one do you recommend, please?
Yeah.
That's a good question. So, for the index, let's start from the easy part. For the index, any choice is good. Well, VoltDB is just suitable for one single node, right? If you run on multiple nodes, you have to pick one of the other three. If you run on AWS or Bigtable, unless you are a Cassandra guru, my recommendation is to use DynamoDB or Bigtable. Generally speaking, it's not a big deal. The index is quite small, so in terms of number of items in the index or data utilization, yes, it's significant, but obviously it doesn't contain the log content, right? Getting back to the harder question, there are pros and cons. S3, GCS, and yes, the file system are the cheapest solution. Like, I don't know, S3 can cost 1/10 of DynamoDB, right? And it's a very good solution. I mean, they work very well. They have very good performances. My personal recommendation is start with S3 or GCS if you run in AWS or Google Cloud, because they work very well. Cassandra is one of the two options you have for the chunk storage if you run on-premise or in any other cloud. The file system can also be an option if you run a distributed file system, like Chef. But again, I'm not an expert, so I can't give you much details. I know there's someone using it. DynamoDB and Bigtable are more expensive from a cost perspective. They have, at the end, if you store a bunch of logs, they have comparable performances. The main difference we see is that S3 and GCS are rate limited. DynamoDB and Bigtable are not rate limited, which means if you're willing to pay, you can get the IOPS you need, right? With S3 and GCS, they have dynamic rate limiting. So I think GCS is something like 5,000 requests per second, the baseline. And then if you have a steady workload, they increase the rate limit automatically, right? The problem here is if you don't have a steady workload, so you have one query per hour, okay? But the query you have is super heavy, okay? Process terabytes of logs. It's likely you will hit the GCS or S3 limit because you have the baseline rate limiting, and then suddenly we do a bunch of requests to fetch all the logs, and we hit the rate limit. Don't get too much scared. I mean, you need to have a pretty large scale to hit the rate limiting. I'm mentioning it for full transparency. I'm mentioning it because it's something we do see in our clusters. But again, until then, S3 and GCS are my recommended solution.
Out of curiosity, if you hit a red limit during your query time, does the query fail, or can you cope with the red limiting and take longer to finish it?
Okay, we do have retries at different levels. One of the things I didn't mention, well, is that if you have the query front end and the query front end and each query fails for any reason, not just the rate limiting, right? Like a node failure on the query front end can retry the query. Which is something we can't have if we don't have any service in front of the query, right?
I have 3 questions, will be quick. Support for alert manager, retention period configurable, and data compaction in the storage level.
Okay, are you a Loki user?
Almost.
Almost, okay. Because those are very specific questions. Alert manager, is it possible to set alerts based on logs? Not yet, is one of the things we would like to do. The second question was the retention. So the question here is, okay, we store data in S3, okay? But I don't want to keep 10 years of logs. At some point I want to delete my data. The way the retention works is, Loki has a component called the table manager, which I didn't mention. It's the only service I didn't mention in this presentation, right? All other services have been mentioned. I didn't mention because it's a very small component. And what the table manager does is, given the index store use a key value like a big table or DynamoDB, the table manager creates the tables or Cassandra for the index store. So that you don't have to manually create tables or manage them or stuff like this. And the table manager also implements the retention, which means is able, if you enable the retention, it will delete the oldest indexes from the index store. But what's about the chunk store? For the chunk store, it depends. Sorry, I need to go back. Okay, it depends on which storage you're using. So if you use Cassandra Bigtable and DynamoDB, the table manager implements the retention as well. If you use S3 and GCS, Bigtable doesn't support the retention, and the retention is usually implemented just using a bucket policy. So S3 and GCS allows you to configure a bucket policy, which is just a rule which says, okay, all the objects, the data, older than 1 year should be automatically deleted. That's the way we do implement the retention for S3 and GCS as of today. The reason is because AWS and Google are much more performant into running queries within their own service than having us externally firing millions of queries to delete every single object. The third question was?
Data compaction.
Data compaction. What are you specifically mentioning there?
I'm just asking about Cassandra and how it affects the chunks and the volume of the storage that you need to provide for the Loki when you're storing the logs.
Okay. So I personally don't have experience with Cassandra. In our use case, we use Google, so we run on GCS and Bigtable. The data side, the storage side, is mainly impacted by the compressed logs, not by the index, but the compressed logs. You can configure in Loki the compression algorithm you want to use. So the best compression is given by gzip. The problem of gzip is that it is slower than other algorithms with the support, so it's a trade-off. Usually it's between, I think, 4x, 10x the uncompressed data. So if you look at 1 day of data, you calculate the size of the compressed data, and you have a rough idea of the storage you need based on the retention you want to keep.
Thanks. And last question. The Grafana and alerting in there. So we have seen that you can provide the metrics from the Prometheus.
Mhm.
So I suppose that is also you can define the alerts in Grafana for the Loki.
We have 2 people from the Grafana team here. Please stand up. Because I don't know the current state of the Grafana alert with the logs.
Yeah, that's unfortunately not implemented yet. So basically the part where you can do metric queries on Loki was implemented later on. So we still didn't implement the backend for the alerting on that part, but it's also in the future roadmap.
It's wrong. Okay, thank you.
And then Prometheus is, when the Loki Prometheus is running in Kubernetes, the Prometheus is running as a sidecar in every pod, or it is deployed on every node in the cloud? How the Prometheus is
Sure.
running in Kubernetes?
So the question here is, I run my applications on Kubernetes, how can I run Prometheus to scrape the logs? We recommend to run Prometheus as a daemon set. So 1 Prometheus per node. It depends where your Kubernetes cluster is running, but if you run on AWS, GCP, GKE, the Google Cloud, or on-premise, obviously, you actually have access to the host file system where the logs are stored, so it's not a big deal.
And when I have an old style application which has multiple logs,
Which? The
some
application?
old style application which is not logging to standard output but has on the file system more logs, log files.
Oh, sure. Prometheus tails the logs from the file system. So yeah, you can collect the logs from legacy applications as far as they log to the file
The
system.
demo set can go to every pod, to the file system and scrape log.
Mhm. Yeah, that's one way to run it. So your legacy applications are running on Kubernetes? Yes?
We are trying to do that.
Oh, okay, so if you have your applications running outside Kubernetes, you can log the applications to the local file system and then Prometheus script the log. If they're running inside a pod, one option is to, configure the logging to log to the file system and then Prometheus scrape each pod log to the file system and then Prometheus scrapes them. Third option is using the Docker driver under the hood. If you're using the Kubernetes with the Docker as container engine, you can configure the Docker driver to directly pick the logs from all the containers output.
Is there some like authentication and role-based access?
Okay, so how does the authentication work? The answer is no. Loki doesn't provide built-in authentication. If you run if you run in a single tenant mode, you can just, we usually suggest to put a reverse proxy like Nginx doing authentication in front of it, something like this. If you run in the multi-tenant mode and you actually need to authenticate the user and then to inject an HTTP header with the tenant ID, with the user ID, which is used by Loki to know which is the tenant, which is the user, which is doing the request. There are some open source solutions. We have, to give you an example, at Grafana Labs, we have a closed solution, and the reason is pretty simple. You usually want to build this authentication system based on your internal authentication model. Like in our case, we have our solution based on our own specific use case. What you need is a proxy in front both of the distributors and the query or the query frontend, which authenticates the request. And if you run in the multi-tenancy mode, you need to inject an HTTP header with the tenant ID of the authenticated user.
So I will interrupt you. You can find Marco here. I have last question to the public. I can imagine that in big environments, big deployments, there should be a lot of messages to sort and collect. And is there any advice how long I should keep, how many days backwards I should keep the logs? Because usually when something is 15 or 20 years old in the logs, so it shouldn't care anybody. But when errors happen, because logs isn't important if everything working well, you know. But if somebody need to look backwards, what happened there or there, how in your opinion, how many days or hours or weeks we should keep the logs?
Right. So what's the suggested retention? Basically the question. It depends on your use case. If you're collecting system and application logs, probably 30 days is more than enough. I mean, if it's 30 days, you have a production issue and you didn't figure out yet, well, probably is not that much important, right? To keep 31-day retention. There are some specific use cases where you may want to have a very long retention, like security policies or regulation. I don't know specifically the GDPR to give an example, but I think you have to keep the data for, not the GDPR, there are some other European regulation about the access logs and stuff like this. But you have to keep the data for quite a long time. In that specific case, you may actually also want years. Like you want to be able to go back years into your access logs.
Perfect. Thank you, Marco. Thank you for providing us a speech about the entry level, then go through the demo, and then go through deep dive, a short deep dive, of course, and see maybe later. And you can catch him anywhere, anytime, any place. Thank you.
Thank you.